back to another discrete math tutorial. This time we'll focus on logical equivalences involving biconditional statements. Let's go ahead and start off with the first one. So P if and only if Q is identical when P implies Q and Q implies P. This is actually a very straightforward equivalent. Remember, in an if and only if, you have to prove that P implies Q and then also reverse the direction that Q also implies P are true. If P is true and Q is true, then both are true. And then go in reverse, you'll just put this here, and that becomes true. So looking at this statement, P implies Q, and then also the reverse, Q implies P. And then that is a conjunction, because you have to have both. P implies Q and Q implies P. The next one going down is P if and only if Q is equivalent to not P if and only if not Q. So basically this is stating that we're just gonna, whatever this is, we're gonna take the opposite values of these, and that's gonna be identical to whatever this produces. So let's look at something quick. Let's say true and true. True implies true is true. Going back the other way, true implies true is also true. Well, here, the opposite of true is false. False implies false is true. Going back around, false implies false is true as well. That's true and true. And so you can see that these two statements are, as a matter of fact, equivalent. Looking at the next one, we'll look at P if and only if Q is equivalent to P and Q, or not P and not Q. Okay, so let's see if we can think about this. So P and Q have to be both true, right? So in order for this to be a logical expression, if we wanted to either have true or false, let's say if we wanted this statement right here to be true, we said P is equal to true and Q is equal to true. That's the only time that this statement can be true, right? So true and true is true, or, well, the opposite is false and false. Well, true or false is true. So that is equivalent to this. Similar, if you set both of these to false, well, the opposite then of these is true. Well, true or false, again, comes out to true. And if we wanted to look at it from this side, if, for example, false implies false, well, that's true. Implies false from the other side, that's true as well. So true is equivalent to true. And the last one we're going to look at is the negation of P if and only if Q is equivalent to P if and only if not Q. This one looks like it'll be tricky, so I think the best way to do this is with a truth table. So let's go ahead, since there are only two variables, just to kind of illustrate that these are equivalent, is P, Q, then we have, we'll go ahead, P implies Q. Well, let's actually do P if and only if Q. We also have the negation of that entire thing, not P if and only if Q. Followed by, if we look at this side, we have not Q, and the last one is P if and only if not Q. So true, true, false, false, true, false, true, false. So remember, we're going to be comparing this column and this column. So P if and only if Q. Remember, the values, the truth values have to be identical. So true if and only if true is true, because true implies true. And if you reverse it, true implies true as well. This is false, this is false, and this is also true. The negation of that, of this column, is just the opposite. So false, true, true, false. The negation of Q would be false, true, false, true. And basically P if and only if not Q. Basically we're going to be looking at P and not Q. So they're opposite right there. So that's false. So true, true, true. False and false is also true. False and true is false. So if we look at here and here, these are all identical values. Many different ways to prove these. We just picked the truth table for the sake of time and just to really quickly demonstrate how this equivalence is actually accurate. We'll go ahead and stop this tutorial right here. I hope you guys learned something, and make sure to subscribe to my channel for more discrete math tutorials.